Good afternoon. How are you?
I am good. I am good. So working
Great.
on Saturdays as well.
Yeah.
Okay.
Yeah. So I think we have to make our country a developed country. We have to work.
Yes. On the line of Narayan Murthy ji.
Yeah. As he mentioned.
Yeah.
So the participants are joining. We can wait for 1 or 2
Okay.
minutes.
No problem. No problem. So I
Right.
would be sharing my screen from my side. No?
Yes, yes, you can share the
Okay.
screen.
Okay. So I will share. Let's all of them join. Then I will
Yes,
share
yes,
my screen. We'll
yes,
start.
yes. Right, right, right.
Okay.
We have made your Saturday also. We have occupied your Saturday.
It's okay. It's okay. I am also part of country na, so can contribute for the growth of the country.
You are already doing a lot.
Thank you so much.
uh,
Everyone is doing. Everyone is
no, no,
doing.
you are making these semiconductors policies, and you are actual the one who is bringing this semiconductor and the manufacturing part of in India, which we were lagging. I would say.
No, no, no. Actually, all of us are part of ecosystem only. You are contributing at academia level. I am contributing at
Mhm.
industry, or you can say association level. So everyone is contributing, and even in this space, I will say that one only can't do anything in this space. So everyone has to come
Yes,
together and
yes.
has to
Right,
contribute.
right.
Yes.
So we had a 6 day long FTP. We had
Right.
a sessions from Professor Lee. Very wonderful session, I would say. He actually gave the participants how the practically he shared the
Mm,
patents and how they were implemented and how the packaging is done in iPhone 5, 6, 7. He showed
mm.
those things. That was very informative session.
Actually, what I was also thinking that this space is something like that you can't cover each and everything in 1 hour. Means
Yes.
it would be only a bits of that.
Glimpse
So
of that, yes.
if I will touch only one topic, then also it is very less to like say.
Yes.
So that's what I was also like. It was challenging for me as well that what to put in the presentation and what to not. So
Right,
actually,
right.
it has to be, and I also means very much like curious about to know that who are the listeners, whether they are faculties or
They are
students, or it's
the
a mix of.
they are the faculty and the industry experts. But
Okay,
maximum I would say academia,
okay, okay, great,
right? Research scholars, academia, and the industry.
okay.
So
So because the kind
this
of
is
work we
sponsored
are
by
doing.
the AICTE.
Mhm.
So in semiconductor domain only, they have selected 149 FTPs all across the India, and we were the one of them. We
Right,
applied many, but
congratulations.
thank you. So this time the semiconductor was one of the theme for the
Right.
FTPs.
Yeah,
So they have selected 149 FTPs in the semiconductor domain.
demand
They
of
have
time.
received a huge response on this, and proper scrutiny has been done to select
Okay.
the FTPs but based on the topic,
Hmm.
content we are covering, and the speakers, the resource persons.
Right, right.
So we had two international resource persons. One was Professor Lee, another was Dr. Vinay. He was from the
Okay.
Northern
Yeah,
Illinois
yeah.
University.
Yes, yes, yes.
Yeah,
I know him. Yeah.
you know,
Professor Lee
yeah.
also we know from
Yes.
okay.
Professor Lee also, yeah.
Yeah,
And
yeah.
from national, we had Professor JP Singh from IIT Delhi. We
Okay.
had Professor VV Rao. You
He
might be
was
knowing Professor
yes,
VV
yes.
Rao.
Yeah, he was there
Yeah,
in SSCI.
yes, that in at IIT Delhi. One was Dr. C. Ramachandra. He's from the ISRO, Director ISRO. Then we had many speakers. The- One was Mr. Shubham Jain, our alumni, I would say. You are muted. You are muted. Uh-huh.
Okay. I was just saying that listening to you, I am thinking that I am the junior most, maybe least knowledgeable.
No, not at all.
Okay, let's
So
see.
our opening session was by Dr. Satya Gupta.
Yeah, that I know. I
Uh,
joined for a while in that
yes,
session.
yeah. And the closing will be by Mr. Anurag.
Anurag. Yes, yes, yes.
Right. So
So
I
shall
think we
we
can
start?
start. We can start. Loxy and Yesi, I would request you to please take it forward to welcome Dr. Aki. Loxy, where is she? Just give us a minute.
She is mute. She is muted.
Hello.
Yes, yes. Now you are audible.
Okay, ma'am. So, good afternoon, everyone. A warm welcome to day 6 of the 6-day online ATAL Faculty Development Program on Vacuum Technology in Semiconductor Manufacturing and Packaging, Innovations and Applications Challenges, organized by the North Cap University, Gurugram. As we reach the final day of this insightful journey, we take a moment to appreciate the valuable knowledge shared over the past 5 days. Each session has deepened our understanding of the critical role vacuum technology plays in semiconductor manufacturing and packaging. Yesterday, on day 5, we have two enriching sessions on leak detection and system integrity, and another one was vacuum measurement and control, which provide us with practical insights into the process stability and system optimization in vacuum environment. So, as we step into our last day, today's discussion will focus on global semiconductor market, contamination control in vacuum environment, and emerging opportunities in semiconductor technology. So, let's begin this final day with the same enthusiasm and curiosity that has driven us throughout this program. So, our first session today will provide a broader perspective on semiconductor market, that is global landscape and growth perspective. So we are honored to welcome Dr. Rakhi Nagia, Deputy Director at Indian Electronics and Semiconductor Association and Semiconductor Fab Policy Advisory at the Ministry of Electronics and Information Technology. Dr. Nagia bring extensive expertise in semiconductor policy making, market trend, and the strategic vision shaping the future of this industry. In this session, she will offer key insights into the global semiconductor ecosystem, market drivers, and India's positioning in this rapidly evolving sector. Her discussion will highlight growth opportunities and the impact of policy initiative on semiconductor manufacturing. So we invite Dr. Rakhi Nagia to take the virtual stage and share her expertise with us. Over to you, ma'am.
A
Thank
very
you,
warm
Roxy.
welcome, Dr. Akia. So you can please take it forward.
Okay, thank you so much. So, first of all, I would like to thanks the North Cap University for inviting me for this AICT workshop, and I want to thank everyone who has joined here, uh, who is spending their Saturdays and the time to listening these things. So, first of all, congratulations for that, and as Loxy shared that I would majorly focus on semiconductor market, the global landscape and opportunities. So I would like to like I would like to get you explored regarding what are the different scenarios globally and what is the scenario in India in the like field of semiconductor. As you know that semiconductor is very niche for India. So I will share with you the total perspective uh, with the global landscape. So with that regard, I would like to share my screen and will start. So I would like to ask Pooja ma'am, can I share my screen?
Yes, you can please.
Okay. Can you see my screen, ma'am?
Yeah, we can see the screen.
Okay. Okay. So, as I just mentioned that, okay, I think I should start with this picture. So everyone, I think most of them can't speak in between, but you can at least see that in this picture, what you can see in the picture, we can see that in our day-to-day life, there are various appliances, consumer electronics, digital products, various like high-tech devices, for example, Alexa, various consumer electronics like washing machine, smart TVs, smart fridge, and various digital products like laptops, desktops, hearables, wearables. So each and everything means thousands of electronic, means at least hundreds of electronic devices around ourselves. And in those electronic devices, there are in those electronic like consumer devices, there are electronics inside, means there are semiconductor chips inside. So can you imagine how many semiconductor chips on a daily basis we are using? So I will say in each and every home nowadays, there are thousands of semiconductor chips that are residing in each and every like modern day home, which every person is using, and maybe they are not aware that they are using so much of electronics, and inside the electronic devices it is nothing but semiconductor chips. So, and that is creating the semiconductor market. So let's come to the next slide. So this slide shows the growth of electronics manufacturing in India. As I just mentioned, that we are using lots and lots of semiconductor devices in our day-to-day life. You can like relate with your day-to-day life how much devices and electronics and smart products we are using. And because those semiconductor devices are going into electronic devices, means the final product. So that's how it is driving the electronics manufacturing in India. So as you can see from the graph, that domestic, the demand of electronics is nearly 179 billion USD dollar in 23-24, and it is going to be 300 USD billion dollars by 2026. And from the below graph you can see that which are the major demand drivers. So you can see that there are mobile phones, IT hardware like laptop, desktop, tablets, and other devices as well, means very very smart devices that are being used in offices, in like our work professional life as well. Various consumer electronic devices, TV, fridge, speakers, and means whatnot. Similarly, we are also using auto electronics like various automatic cars, and these things are using thousands of semiconductor chips inside. Similarly, industrial electronics, for example, there are various servers data storage devices, wearables, hearables, electronics components. So these are the demand drivers who is driving the electronics manufacturing in India, and that's how India is targeting 300 billion USD manufacturing in India itself. And by 2030, it is not less than going to be 500 billion US dollars. So it has come in various reports as well. And Ministry of Electronics has also come up with their like roadmap for this 500 billion electronics manufacturing in India by 2030. So as this is electronics manufacturing, so that is driving the semiconductor market opportunity. So as this graph is showing that we in 2020, the semiconductor market was nearly 15 billion USD dollar, but it is in 2025 and in 2026, it is somewhere nearly 64 billion dollar, and it is expected that by 2030, the semiconductor market is going to be 110 billion US dollar. And the major emphasis here, I want to say that the global semiconductor market is going to be 1 trillion US dollar. And see, in 2020, the Indian semiconductor market demand was 3% of the global demand, while by 2030, it would be 10% of the global demand. So you can see from this, means you can relate from this graph that demand, India's semiconductor demand is increasing day by day. And instead of 3 to 4% as compared to the global demand, it is going to be 10% by 2030. So you can imagine like how much semiconductor would be needed in 2026 to 2030 and maybe in other years as well. Okay. And as I just mentioned, that various demand drivers are definitely so much electronics, smartphones, wearables, hearables, automotive, compute, like AI, data storage, IoT. You can see various homes nowadays, various modern homes are using a lots of like Internet of Things. Every device is connected to the internet and is being smart and smart on day-to-day basis. Similarly, the 5G communication. So each and everything is using semiconductor devices, and that is driving the electronics market. So it is again the bifurcation of the market only. So here I want to show like out of those what I just mentioned, that these are the various demand drivers. So out of those demand drivers, which are the major one? So if we can relate with your daily life, that yes, the mobile phones, hearables, wearables, various IT gadgets like laptop, desktop, mobiles, these things, and 5G and these networks, these are contributing most of the market. So you can see from this graph that in 2021, if the total market was $27 billion, then these mobiles and wearables was contributing 13.8 US billion dollar, means nearly 40 to 50% of the total market is driven by mobiles and wearables and wearables. And similarly, the trend will goes on. In 2026, nearly out of 64 billion US dollars, 31.5 US billion dollars is going to be driven by mobiles and wearables. And next will be driven by IT, and then by telecom, and so on. So these are the various, and inside those means mobiles and wearables, there are various types of components that are being used in your mobile. There is a processor, there is a memory, there is various PCB, small and small, which is used to connect to power, to various other connectors, and so on. Various sensors are there, cameras are there. So these are the market by component. So out of means total market, what would be the like bifurcation component wise? So this would be the not approximate, but the estimated bifurcation of the components for market wise. So from this slide, I want to show that where we are lying. So if everyone can relate, if someone as I get to know from Pooja ma'am that most of us are from industry, from academia, so everyone at least relate these devices, how these are being manufactured. So when we start from simple sand, so it is not a very simple process that only sand is going to produce the silicon ingot, but it is a very tedious process. Lots of high purity silica is needed to produce this silicon ingot. Then this silicon ingot is diced into bare wafers, and these bare wafers then fabricated in a semiconductor foundry. And when this wafer is then being cut into, for example, it is a 200 millimeter wafer or 300 millimeter wafer, so it may have from 1000 to 2000 chips on a single wafer only. So depending upon the complexity of the chip, depending upon the size of the nanometer technology, if it is a 3 nanometer chip, it is a 7 nanometer chip, or it is a 180 nanometer chip maybe. So depending upon the technology, a wafer of 200 millimeter to 300 millimeter of size may have 1000 to more than 1000 of chips in a single wafer. And then each individual chip is being cut from this wafer and then being packaged here. So what I wanted to show from this slide, that this bare wafer is being imported in India, and then this wafer is being fabricated in a semiconductor foundry, right? And when this fabricated wafer will get out from the semiconductor foundry, it will go into a ATMP, like OSAT unit, outsourced testing assembly unit, means packaging packaging facility. So that's how a semiconductor chip will be in your hand, and this chip will go into a final product, a semiconductor like PCB or electronic device. Then that electronic device will get a electronic product, and that's a product that you are using in your hand, maybe a laptop, desktop, or mobile, or somewhere like your consumer electronics, fridge, etc., etc. So as of now, India is very niche in this market. As of now, we are not producing any semiconductor wafer. We are not producing any fabricated wafer. We are not even doing packaging, right? So the journey has just begun. And now, in the further slide, I will show you where India is and where the globe is, right? So it is the complete semiconductor supply chain. So what do we understand by semiconductor supply chain? As I just showed in my previous slide, so this is only the manufacturing, right? How a semiconductor chip is being manufactured. But when the chip is being fabricated here, the design has to come from somewhere. It is only the manufacturing process in a foundry, but it is earlier it has to be designed in a design phase. So this is the design phase that is usually being done in various like companies that we used to call the fabless companies, where chip design is their major focus, and then the foundry where the fabrication is being done, and then the OSAT unit, or we can call it assembly, testing, and packaging unit as well. So this is the complete supply chain of semiconductor, that the first the chip will be designed, then the design will be fabricated on a semiconductor wafer, and then that wafers will be cut into various chips, and those chips will be packaged. And these are the various allied sectors that would be needed for design. What do we need? I think most of us would be knowing that if I am doing a chip design on a laptop or desktop or in an industry, what do I need? I need various electronic design automation tools and core IPs. And there are various companies like Synopsys, Cadence, Mentor Graphics, who are designing the EDA tools, and those EDA tools are used to design a semiconductor chip in this phase only, right? Then coming to fabrication phase, what are the different things that are required for fabrication phase? So number one is the raw material. Raw material includes wafers, includes chemicals and gases, and these are not common chemicals and gases. I will let you know in further slides. And the most important thing, which is the most capital intensive, is the semiconductor manufacturing equipments. For example, lithography equipment, deposition, etching. So these are the various equipment that are used to fabricate a chip. So it is a very, very complex and very, very labor intensive and very, very complex process that is being used to fabricate a chip. It's a very complex, I will say. So it's a very technology intensive, and India has just entered into this space. And coming to packaging, so this is not as complex as fabrication, but yes, it is also a very complex process, because nowadays we are not only talking about the conventional packaging, but the advanced packaging like 3D stacking or various wafer, like single chip wafer, and so on. So there are various complex things in the whole ecosystem, I will say. So this is a complete supply chain starting from design to fabricate to packaging, and uh, means all around this is the research and development. So at every phase, R&D will go along. So you can't exclude any of the phase without R&D, because, for example, if some foundry is working at a 45 nanometer now, but but after a few years, it will be a obsolete node, 45 nanometer. Samsung and TSMC, these are the biggest foundry. Those are working at 3 nanometer technology as of now. So this is the latest technology that is being used. So the research is already being done. R&D is already being done at various cutting edge nodes. Those are 3 nanometer to 7 nanometer node. So right now, India is majorly focusing on 28 nanometer node. Considering it a sweet spot for India. So I guess this supply chain is clear to everyone. So it means maybe after this session we can take 10 to 15 minutes Q&A. You can like raise any query. So from this slide, I want to show you the various semiconductor companies by revenue. These are the top 15 companies globally which are present in the semiconductor space. And from this, you can see the companies, their headquarters, their business model, and revenue. So for now, you can exclude this because it is not related to you to understand. But this business model is very important to understand from the point of view that, as I just mentioned in my previous slide, that some companies are only designing, while some companies are only manufacturing, while some companies are doing end-to-end process, means they are also designing, they are also manufacturing, they are also packaging. So those companies are called integrated device manufacturers, so called IDM. So Intel, Samsung, SK Hynix, Micron. So the company in front of which it is written IDM means they are doing their end-to-end process. They are designing their chip, they are manufacturing their chip, and even they are packaging and then using in their own products as well. And some companies are only doing design only. For example, NVIDIA only designs the processor, GPU processor. Similarly, other companies, MediaTek. So these are, yeah. And AMD, AMD is producing GPU processor, etc. So these are the different models of the companies. And from this, it is very important to see that from this you can visualize that most of the companies are either present in USA or in Korea or in Taiwan or in Europe or Japan. Nowhere you will see India. Yeah. So from this, you can just imagine that India is nowhere in this space as of now. But yes, we are going forward. So in this slide, you can see, as I mentioned, that designing EDA tools, materials, wafers, chip companies, foundries. So here are, I think, Pooja ma'am, can you see the screen in a proper way? Means the font size is okay?
Yeah, Rakhi ma'am, it's perfect. Yeah.
Okay.
Yes,
Okay.
thank you.
So from this, I wanted to show that there are various companies which are present in these domains. Few are producing intellectual property, few are developing electronic design automation tools. Few companies are only working on materials. Few Japanese companies are producing raw wafers. Few companies are designing the chips. Few are IDMs and few are foundries. Means they only fabricate, not design, not package, right? But all of these companies are present globally. Most of the companies, there are 6 and 7 geometries which are like major ones in this space. So I will say the US, the major one, then Korea, having the SK Hynix and Samsung there, then Japan, which is has their monopoly in terms of producing the wafer, then China, and similarly Malaysia. So means there are 6 and 7 geometries which are majorly contributing to this ecosystem, and India is just entering into the space. So from this, I want to share that where we are actually. So this is the domestic value chain, as I was saying, design, equipment and tools, and manufacturing. So where India is lying in terms of design. So I think every one of us know that there are various chip design companies in India, but none of them are Indian. They are multinational companies and using Indian workforce to develop and to design their chips, but the intellectual property remains with the company headquarters, with the company only. For example, Intel, there are means company presence in Bangalore, company NVIDIA, AMD presence in Bangalore, maybe, and some other companies, for example, NXP having their presence in Bangalore, in Noida, ST having their presence in various cities of India. We are designing only for these multinational companies, and the intellectual property is of that company only, and it is not called of India, of Indian IP, right? But the major advantage of working in this domain that 20% of the chip designers are Indians. So we can say that India knows to design the chip. So in terms of workforce, in terms of knowledge of chip designing, India is contributing 20% of the global manpower. So 20% of the world design engineers are Indians, whether they are sitting in India, whether they are sitting in any other country. In terms of equipment and tools, there are five major firms which are producing semiconductor equipment tools. The major ones are Applied Materials, Lam Research, KLA, and there are Tokyo Electron, others as well. And everyone has presence except Tokyo Electron, Applied Material, Lam Research, KLA. They have their presence in India, but they are doing their R&D here, not manufacturing. So they are not manufacturing equipments and tools in India, but they are doing their back R&D engineering in India. In terms of manufacturing, as I was mentioning, that there is no commercial fab as of now, but there are some strategic fab in India. The biggest one you can say is the semiconductor laboratory. It is having its presence in Chandigarh, Mohali, and right now they are working on 180 nanometer technology and is producing chip for various strategic purposes, for various defense purposes, for various other strategic purposes. But yes, the technology, if I will say from technology node perspective, so we are far behind, right? And similarly, there are other small, like a strategic fab. Sitar is there, GATEC is there. So these two fabs are under Defense Research and Development Organization, DRDO. Similarly, there is a few packaging units, CDIL, it is again in Mohali. It is beside SCL only. So they are producing discrete like devices, for example, thyristor, transistor, these. So discrete component devices they are producing. Similarly, SPAL is there. They are doing packaging. Is always there. They are working on test equipment, etc. So I will say that in means if I will talk about India or domestic, so we do have presence of components of some semiconductor supply chain, but it is not as desired in terms of if I will compare it globally. But we are starting, we have initiated the thing and is going ahead with the policy and this thing that I will just tell you further. So these are the 7 state-of-art nanofabrication facilities. So as I was mentioning here that we are having few strategic fabs. So we are having some R&D fab as well. We can say it not commercial fab, not very low level fab, but it is lab to fab kind of setup that we are having in 7 nano centers. So these 7 nano centers are nothing but 6 IITs and 1 IISc. So these 7 state-of-art nanofabrication facility, and they are working not at 200 nanometer wafer, but yes, 4 millimeter wafer they are working, and they are producing chips. For example, IISc working on GaNFab project, gallium nitride, that is a compound semiconductor project, and these 7 means facilities are being funded by Ministry of Electronics and IT for various research products. So I'm showing this thing that we do have our presence in R&D as well. It is not commercial fab. It is not a very low level lab, but it is in between lab to fab kind of setup where various researches in terms of silicon semiconductor, in terms of compound semiconductors are going on, and various projects are being worked on, and it is being funded by various ministries from Department of Science and Technology. So yes. And these facilities also do have their collaboration with their international counterparts, and various kinds of exchange programs, faculty exchange, student exchange, and facility kind of like sharing. Those things are already going on in these facilities. So this all everything I am showing from the perspective that what is present in India as of now. So this is the next one, that in terms of design and startup ecosystem, India do have its presence. India has designed nearly 2,000 Indian chipset designed. We do have nearly 20,000 semiconductor design engineers. We are having 35 plus semiconductor design companies, and those are means expanding rapidly because of various government support, various schemes of Ministry of Electronics, and not only Ministry of Electronics, various other ministries as well who support various allied sectors. So they have come up with their other schemes and policies who is supporting these kind of companies. Similarly, these seven nano centers and other like IIT Madras, IIT Hyderabad, they are working on Shakti and Vega processors. So India is the fastest growing startup ecosystem, and government is also pushing from the investment perspective. So we can say that the design and startup ecosystem is rapidly expanding in India. And here is the presence in terms of, I will say, workforce. So as you know, for each and every part of the semiconductor supply chain, whether it is design or manufacturing or packaging or the end product, what is basically need. So here, Pooja ma'am, you are contributing a lot. A lots of workforce is needed to work in these type of companies for design, for manufacturing, for packaging. So we do have these much of IITs, these much of triple ITs, NITs, various universities. Every year we are having this millions of graduates. We are having this much of innovation ecosystem, as I just mentioned, that since it is in IISc, it is working on GANFAB project. Sitar and GATEC, they are again working on compound semiconductor projects. For example, GATEC is working on gallium arsenide projects. CMET is working on materials, various latest materials that are being used in this semiconductor space. Sitar is again a strategic fab of DRDO, Semiconductor Laboratory I just mentioned. They are working on silicon CMOS, as well as they are working on MEMS technology as well. And these are various government programs for skill building. INUP is the program of Government of India that is supporting those 7 nano centers that I just mentioned. Similarly, ESSCI is the Electronic Sector Skill Council of India. So they are developing various curriculums for this space. They are developing curriculum for packaging. They are developing curriculum for semiconductor foundries to develop the manpower, so that on those curriculums, manpower can be trained and they can be get ready to work in these manufacturing and packaging facility. Similarly, there is another program. This is called Special Manpower Development Program, or we can say chip to for chip to system design. It is called C2S program. So it is again an initiative of Ministry of Electronics, wherein the government of India is giving support in terms of EDA tools and various infrastructure support. For few of the, for 100 institutes, they have given the means grant as well. And other than 100, they are also giving the EDS tool support, means the EDA tools from Synopsys, from Mentor Graphics, from Keysight, from Cadence. So these tools will be given at a very subsidized rate or at complementary basis to the institutes who will apply for this scheme of Government of India. So NCU is one of the university who has been benefited with this program. So this is the scenario that I was mentioning verbally, that semiconductor industry is being driven majorly by US, then South Korea, then Japan, Europe, especially Netherlands and Germany, then Taiwan, then China, and rest of the world. Rest of the world means rest of the countries, right? So US means is the giant in this space because they have lots of all the major EDA tools companies are there, all the major like chip design companies are there, and various other materials we are dependent on US. So almost 50% of the market is driven by the US alone. And then because I just mentioned that South Korea, in South Korea there is Samsung and SK Hynix, so they are taking nearly 19% of the total global semiconductor market. Then Japan sources most of the semiconductor wafers to all the companies in the world, and they are also having Tokyo Electron semiconductor equipment manufacturer, means one of the companies that is a major one for semiconductor equipments. Then Europe, including Netherlands, is having ASML. ASML is again a semiconductor equipment manufacturer, which is producing the photolithography machine. And for 2 or 3 nanometer node, that is the only company which produce the photolithography machine. So Netherlands is having monopoly in that regard. Then Taiwan, all of us must have heard the name of TSMC. So 6% of the total global market is being driven by Taiwan, then China and all. So this is something regarding the semiconductor foundries. The data here has been updated till 2019 only. I couldn't get the time to update it to 23 or 24. So these are the number of worldwide fabs. So nearly in Taiwan in 2019, there were nearly 36 semiconductor foundry. In US, there are some 20. So you may be surprised that okay, if Taiwan is having 36 foundry and US having 20, then why US is the major one? Because they are the chip designers and EDA tool provider majorly. But in terms of foundry, Taiwan is the number one. So till 2023, there was no fab in India, no packaging facility in India. But today we are having and we are initiating. This is something regarding the integrated circuit market share leaders. As I mentioned that top 15 like companies are majorly present in 6 or 7 countries. So if we divide the type of IC, so we can majorly divide the type of IC in 3 types. One is the logic kind of chips, one are analog and memory. So in logic, there are again can be subdivided into PC CPU, mobile CPU, graphical processing unit, then FPGA. So these are the major companies which are working in this domain. For memory, for DRAM is being produced by Samsung, SK Hynix, and Micron. NAND is being produced by Samsung, Kioxia, Western Digital. So these are the percentage that if I will say 100% that how it is being subdivided into these companies. So 33% of the NAND memories are being produced by Samsung. 20% of the means these are the means not very I will not say that only 33%, but yes, approximately 30 to 33%. So this is the kind of distribution of various logic ICs, integrated IC, I will say. So that is being produced by these companies. So you can see the blue ones are US companies, and other which are marked in simple black, they are present either in Taiwan or in Korea or somewhere else, but not in India. So majorly these are present in US and other countries. This is the market share by in terms of type of IC. So if total ICs are 100, then out of those total ICs, the logic ICs contribute to 42%, memory ICs contribute to 26%, analog ICs, for example, D2A converter, A to D converter, these contribute to 14%, and discrete optoelectronics and sensor, we call it OSD as well. So it contributes nearly 18% of the market. I think I have already nearly covered these things. I will skip this slide. So as I was mentioning that top 10 semiconductor equipment suppliers. So I think most of us must be knowing what are semiconductor equipment. I mentioned that various equipments that being used to produce a fabricated wafer. For example, lithography machine, photolithography machine, diffusion machine, ion implantation machine, etching machine, various ion implanters, and there are nearly 60 to 70 kind of semiconductor equipment that are being used in a semiconductor foundry to fabricate a wafer. So out of those 60 to 70 kind of equipments, most of them are being made by Applied Material, by ASML, by Lam Research, Tokyo Electron, and KLA. So these are the five ones which are the major ones in terms of producing the semiconductor equipment. ASML is having the topmost presence in terms of semiconductor equipment. And so you can see that three of the companies are present in USA, one in Netherlands, and another in Japan. And then these five are also having a major presence in terms of semiconductor equipment, that is Advantest, Screen, Teradyne, Hitachi, ASM International. So these are present in Japan, USA, and Netherlands. So these are the top 10 semiconductor equipment manufacturers that supply to whole the world. So it is the means there we were having the names and in terms of revenue. So this is in terms of percentage, how much percentage in terms of semiconductor equipment is contributed by US. So nearly 40% of the semiconductor equipment market is being covered by USA. Then by Japan, 31%, with the presence of Tokyo Electron and Advantest. Then 19% by Netherlands with the presence of ASML, and the next one was this ASM International. Then 2% by South Korea, then 6% by rest of the world. So you can relate from this. Now coming to the other part of the ecosystem is the IP and EDA tools that is very much desired in the design phase of the semiconductor supply chain. So EDA tools are majorly being produced, majorly being designed by Synopsys, Cadence, Siemens EDA, and Keysight. So these are the major producer of the EDA tools, and lots of Indians are working in these companies and producing various IPs and various intellectual properties and EDA tools. And these companies are mostly are of Synopsys, Cadence, and Keysight. All three are USA companies, and Siemens EDA is in Europe. These are the top 15 OSAT companies. OSAT, as I mentioned, that after manufacturing, we package individual chip into a separate package, and then those packaged chip will go into inside a electronic product. So these are the top 15 ATMP or OSAT unit, we can say. So this market is majorly being taken by Taiwan, by China, by Malaysia, and Philippines and South Korea. Here, I will not say that lesser, but yes, US has a comparatively lesser presence with the presence of MCOR only. And other major companies in this space is of Taiwan and China. So because this space is comparatively labor intensive, and lots of manpower is available in Taiwan, in China and all. So maybe that is one of the reason that they are majorly into in this space. So this is a very important foil of the presentation. Uh, we have not to focus at each and every word, but from this foil, I wanted to share that semiconductor is a very integrated kind of structure. Means if US is having its dominancy, nearly 50% of the dominancy in terms of total 50% semiconductor market, but even then, means US can't do everything alone. It has to be dependent on other country for various things, for wafer, for various like packaging, for various things. So I just want to show from this slide that this semiconductor supply chain is a global integrated kind of structure, and every geometry has their specialization in 2 or 3 space, but not in every space. If someone is having their strength in design, they don't have their strength in semiconductor equipment, in semiconductor materials, or in packaging. If some country is having their strength in equipment, maybe they are not having their strength in design, and so and so on. So this is very integrated kind of structure. And to make a very resilient semiconductor supply chain, every country has to collaborate and cooperate with other countries. And that is really the current scenario, that US is collaborating with any other country, or Taiwan is collaborating for other countries for various things. So a, a single chip that is present in your laptop or desktop has roam around the whole world to come to your system, right? From this, I wanted to show that why this is a very technology intensive space, and why it is so complex, and this thing, because to set up a semiconductor fab is not a is not easy. I will say it's very complex. There are various factors of being complex. Number one is the capital intensive. Means to set up a fab, you need billions of US dollars. For example, if India is focusing on 28 nanometers, so nearly 2 to 4 US billion is needed to set up that kind of fab. And if TSMC or Samsung, which they are focusing on 3 to 5 nanometer of technology, and they are opening up their new fab, for example, TSMC has opened up their fab in US. Similarly, US firm is opening their fab in Singapore. But each and individual fab, if they are working on 5 nanometer and below technology, to set up a single semiconductor foundry, more than 10 billion US dollars are required to set up that kind of fab. So one is this. Second is the knowledge, means technology know-how. Not everyone can have that technology know-how for this semiconductor space. And third is the workforce, means skilled manpower. So these three are the big factors that are needed to set up a semiconductor manufacturing unit. Number one is the capital. Second is the infrastructure that must be present in the country. Third is the know-how, means technology and knowledge of technology. And fourth is the workforce development. So these are the various factors, and each and every factor is important in its space. So coming to conclusion, so we have seen from last of the slides that yes, semiconductor is a very complex and technology intensive process. India has some presence in every space, in design, in manufacturing, in packaging, and globally we have also seen that what is there, where means equipments are where, raw materials are where, design spaces where, and so on. Now, to tap this gap, now government of India has come up with their policy to tap this gap and to set up a resilient semiconductor and display manufacturing ecosystem in India. And they have come up with various policies, not only semiconductor policies, but electronics manufacturing as well, means to support this ecosystem. So I think most of us present here would be knowing that government of India has come up with the 10 billion USD dollar policy in 2020, in December 2021, to set up semiconductor and display manufacturing ecosystem in India. So this policy is supporting to set up semiconductor fab, to set up display fab, to set up compound semiconductor, for example, gallium arsenide, gallium nitride, and silicon carbide. So these kind of fabs, ATMP, packaging units. Similarly, Government of India has come up with design-linked incentive scheme and modernization of semiconductor laboratory. So the last one is, as I mentioned, that as of now, semiconductor laboratory is working on 180 nanometer technology node, but going forward, government is thinking to commercialize this and to bring a technology partner who can bring the technology, and SCL can work on 28 to 45 nanometer technology node, because the infrastructure is already there. Only technology has to bring up, and some other allied things will be required. And these other policies are various production linked incentive scheme to support allied sectors and to support electronics manufacturing. So this is the complete Semicon India program. We usually call it the Semicon India program or semiconductor fab policy. Either way, we can call it. So total outlay that has been approved by Government of India is 10 billion US dollars. If we convert it into INR, then it is 76 to 80,000 crore of INR rupees. So for setting up semiconductor and display fab, how much physical support is given by? So nearly 50% of the total project cost that will, of total project cost to set up a semiconductor fab will be given by Government of India on front basis, a front or pari passu basis. Similarly, Government of India also supporting the investors in terms of infrastructure support. Infrastructure, we can count the land, the water, the power subsidy. So not only Government of India, but various state governments as well have come up with their policy to support the investor, like companies or investor, we can say, to give subsidy on land, on water, because these are the things that are very, means to set up that kind of infrastructure is needed to set up semiconductor fab. Similarly, the compound semiconductor and packaging policy, so 50% of the capex is being supported. And these are the additional support that is being given. Similarly, semiconductor design. So this is the design linked incentive scheme. So this scheme is supporting 100 startups, right? So the design infrastructure support and like EDA tool support will be given by, means 50% of the subsidy will be given by Government of India. Similarly, on sales as well. So we call it deployment linked incentive. So 6 to 4% of the net sales means incentive on sales as well will be given by Government of India, and design infrastructure support in terms of EDA tools. And this SCL, Semiconductor Laboratory, so modernization of SCL. So SCL earlier was part of ISRO, but now it has come under Ministry of Electronics and IT, and efforts are being taken to modernize this facility. So this is again the part of a scheme only. So from this like pie chart, we can see that 50% of the total fiscal support is being given by Government of India. On the top of that, 20% of the support is being given by State Government of India, and rest 30% to 35% has to be invested by the investor. So these are the target segments which are being covered under this program: semiconductor fab of every node, any node; display fab where LCDs and AMOLED means there are various nitty-gritties in this scheme, various guidelines are there. So this is on the broader level I am just telling, because there is no benefit of going into various nitty-gritties of this program. So these are the various target segments that are being covered under this policy. Design linked incentive scheme, I already mentioned. So these are the various target segments that are being covered. So if any like a startup or design company which is like working on integrated circuit, chipsets, system on chips, systems and IP cores, or semiconductor link design. So they would be supported by Government of India in terms of product design. 50% of the support will be given. In terms of deployment, means if some company will develop an IP, and if it would be deployed somewhere by some other company will take that IP and will use it in its product, then on that sale, the Government of India will give 4 to 6% of incentive and infrastructure support. Sorry. So here in this picture, I have shown this picture to just have a glimpse of, means I think most of us maybe knowing this thing, that how a semiconductor fab looks like So most of these process like etching, lithography, and these things are automated nowadays. Comparatively lesser manpower is required in semiconductor foundry, especially in latest technology nodes. However, lots of manpower is needed for packaging facilities. So I have come down one by one, means in a flow, to tell that because this is we are talking about the vacuum technology, right? And what is the application of the vacuum technology? First of all, it is necessary to know that where this technology is going to apply, right? So in every, whatever I have just shown the picture of this semiconductor fab. So everywhere in this fab, this vacuum technology is being used. Either it is a equipment, either it is the total clean room, or either it is any of the equipment, or means deposition or etching or whatever the process that is going inside this semiconductor fab is using vacuum technology. And why vacuum technology? Because in this space we needs a lots and lots of purity. So we usually say semiconductor gate. So what is that semiconductor gate? For example, if I will tell about like for example, gallium, Ga. Gallium is one of the material that is majorly used in semiconductor fab. So for a normal metallurgical grade, maybe it may be of 2N to 3N of purity, or maybe at the max 5N of purity. So 5N, what does it mean by 5N? So it is usually 99.599999. So 5N kind of purity is required for a material to be of metallurgical grade. But for a material to be of semiconductor grade, it has to be of 7N to 9 of N purity. So you can think that what level of purity is required in a semiconductor foundry. And there comes the role of vacuum technology, because in this space, we can't allow any kind of particle, means instead of the particle that is actually required in either in clean room, either in deposition process, in etching process, in ion implantation, wafer handling and transferring, rapid thermal processing, testing, vacuum pumps, and overall the clean room environment. So in at every stage of semiconductor fab, this vacuum technology is required, and that's how means the application of vacuum technology is not less than in a semiconductor industry. So I was yeah. So these are the projects that has been approved till today by Government of India for setting up semiconductor fab and packaging unit. So one of the major project is being by Tata Electronics Private Limited. So their knowledge partner is PSMC. This is the Taiwanese companies who is bringing the know-how how to like develop this 28 nanometer kind of technology. And this project is being set up in Dholera, Gujarat. And the project capacity would be 50,000 wafers per month capacity. And they are working on 28 nanometer node to 110 nanometer node. So this, as of now, it isn't like being developed. So maybe it will take another 2 to 3 years to produce a chip from this facility. So these are other 4 projects that has been approved by Government of India. One is the Micron. So Micron, we have seen, it is the major memory producer in the world. It is a US-based company, but they have come up, they were the first one who came into India to set up a packaging unit, not a foundry, but a packaging unit. Means once a wafer will come out of a semiconductor fab, then they will package it with their latest technology. Another is again by Tata. They are being set up, they are setting up their unit in Morigaon, Assam. So they will produce 48 million dies per day capacity. And similarly, there are another company called CG Power. They have tied up with Renesas and Star Microelectronics for technology. They will produce 15 million dies per day. So these 4 are packaging units, and one is the semiconductor fab. The last one is the Keynes Technology. So they are setting up their unit in Sanand, Gujarat. So yes. So these are the pictures of like when Honorable PM broke the stone and launched these new 5 units. Foundation stone of 3 semiconductor facilities with lots of investment. So these are the details of these units only, like Tata Electronics Private Limited. So they are setting up in Gujarat, Dholera with this much of capacity. They have approved in 2024. They are setting up semiconductor fab facility with an investment of 91,000 crore. And they have collaborated or in partnership with Power Chip Semiconductor Manufacturing Corporation, PSMC, Taiwan. They will produce nearly 50,000 wafers starts per month across various technology nodes that I mentioned from 28 nanometer to 110 nanometer nodes. So depending upon the type of chip, the technology node will be. And they are developing their facility in Dholera, special investment region in Gujarat. Another in Morigaon, Assam. So this is again a strategic reason behind this, that why instead of Gujarat, they have gone to Assam, Morigaon, because the various clusters are being driven for clusters in terms of infrastructure development around the country. There are various strategic reasons behind this. So Tata again is setting up their facility, but it would be a packaging facility, and with an investment of nearly 27,000 crore. Yes. And they will use their indigenous technology. Means for this, they have not tied up or has partnered with anyone else. They will use their own technology to package these chips. And these various packaging techniques they would be using, like wire bond technique, flip chip technique, integrated system design, system packaging technique. So these are the various packaging technologies. Not only these, there are other packaging technology as well. This is for CG Power, the third one, which is coming up for setting up their packaging units. So they have again been approved in Feb 2024. They are setting up in Sanand, Gujarat, with an investment of nearly 7.5 thousand crores. And they would be using wire bond and flip chip and hybrid BGA technology to package their chips. And they have joined hands with the Renesas and USK Star Microelectronics. This is for Micron that I said that it is they are the first mover which came to set up their packaging unit in Gujarat. And they will, because they are in memory, so they will produce DDR4, SDRAM, NAND, SSD package, and they are bringing their own supply chain because they will design, then will bring the chip here, will package here, then will sell. So with this picture, I just want to show that not only policy in terms of capex, as I told you, that not only capital is required, but infrastructure and workforce and technology know-how. So these are the 4 factors that are required. So yes, from capex point of view, government is supporting in terms of incentive. For infrastructure as well, government is supporting that various clusters are being driven by other policy. As I mentioned in my slide, that except those 10 billion USD dollar, other 7 and 13 billion US dollars are for other policies for electronics manufacturing clusters. So EMC is another scheme of Government of India, which is supporting development of clusters, is infrastructure. As I mentioned, that to set up a semiconductor fab, various raw materials, equipment, these are needed, but not gallons of waters, very high purity water is also needed. gigawatt of power supply is needed in a semiconductor fab, and that too uninterrupted. If a single second, if power will fail, billions of loss will be there. So uninterrupted power supply is also needed, and lots of land is also needed. So that is being supported by various other schemes and policy of various ministries. So electronics manufacturing cluster scheme is again production linked incentive scheme to support other allied sector, for example, chemicals and gases, other equipments, other things that those are needed. And similarly, this is the last slide of mine for workforce development. So government is also focusing on workforce development. As I mentioned, that Chip to Startup program is one of the major program that is generating nearly 85,000 of manpower. Similarly, other various programs of Electronic Sector Skill Council of India, INUP program, similarly PhD Vishwesharya scheme, and INUP program that is being driven in various IITs and ISCs. So there are various things that are being taken care for capacity development and workforce development in this space. So out of those four major factors, uh, like investment that is being taken care, infrastructure is being taken care, workforce development is being taken care. But yes, there are lots of gaps. And here is the role of academia and research institute. So I will drop my I will end my session here. So how we can go forward in this space. Maybe if you are a student, so definitely join institute or university or college who are offering which is offering semiconductor programs in terms of design, in terms of semiconductor manufacturing, means foundry, in terms of semiconductor packaging. Or if you are a pass out student, maybe you can join various courses of different training institutes. There are various lots of programs that is going on in India. I know various institutes, those are offering exactly the same program that industry, that kind of manpower industry needs. So usually we talk about the academia to industry gap. So that gap is being taken care by various not only a training institute, but nowadays academia as well, various universities, and NCU is one of the university who is moving forward in this direction and has come up with various courses in terms of semiconductor space. So what should be our role in this space? You have to think about this, and there are lots and lots of opportunity in this space. If you want to go in design space, lots and lots of companies are there. I just I have not mentioned all kind of design companies here to it would be that's what I was just mentioning in the space, that I was it was really challenging that what to put in the slide and what to not. So lots and lots of opportunity in this space in terms of design, in terms of manufacturing, in packaging. There are 5 units has already been approved, and various are in pipeline. So at least nearly 10 semiconductor unit will be in India in next 4 to 5 years. So lots of opportunities for students in this space. And with this, I will end my session. Thank you so much for giving me the opportunity. So Pooja ma'am, over to you.
Thank you so
And
much. Thank you, Dr. Aki, taking out your time from your busy schedule, I would say. And your last slide, billion chips, billion dreams, is a
yes,
tagline of the day. Thank you so much. And participants, if you're having any questions, please write in the chat box. It was a wonderful session. I would say eye opener for many of us that what
thank
the
you.
government of India is doing.
Yeah. So that's what I wanted to bring up in this because I got that opportunity to open up in this lots of audience are there that technology is one thing, but first of all, we have to know that where the application lies of that technology.
Right.
So that's how we can relate with the things that, okay, where we are going to finally land up with this technology. So that's how I relate the vacuum technology with the semiconductor market. And so that was my
Right.
motive of
Yes,
this
yes.
session.
Right. So have you have actually set up the, I would say, the tune what we had been learning from since so many days, that why it is required, what is the
Mm.
actual application, why we are doing all this. So any questions from any participants? You can please write in the chat box. Okay, we can take it forward. Loxy?
Yes,
Ma'am,
ma'am.
instead of Loxy, I would seize this opportunity on the behalf
Okay.
of the entire, faculty fraternity present here. So I would like to thank Dr. Rakhi for presenting a holistic picture of the semiconductor setup in India. Professionals like her are working tirelessly towards India's semiconductor mission. On behalf of the entire nation, we extend our best wishes to the faculty fraternity, especially attending this FTP, and the dedicated team players like Dr. Nangia for their success in this mission. Dr. Ramachandra, one of our former speakers, is also joining us daily, enriching our discussions with his valuable insights. A heartfelt thanks to our senior members for paving the way for their knowledge, dedication, and mentorship, leaving a lasting impact for future generations to follow. Their unwavering commitment continues to inspire us and shape the path towards a thriving semiconductor ecosystem in India. Thank you, everyone.
Thank you so much, Tangia. Thank you.
So may I take your leave?
Yes, please. Thank you. You have given us your time. And I
Thank
know
you.
you are preparing towards your summit, and it was a crucial
Yeah,
time. And thank you. I really appreciate. And
no
thank
problem.
you so much once again.
Thank you. Thank you, everyone present here.
Yeah.
Have a nice day. Bye-bye.
Bye bye. Thank you. Our next speaker is here, right? Dr. Anu?
Yes, ma'am.
Yes, yes, he's here, and I'm giving the presenter rights to Mr. Rajesh Yadav.
Right.
So yeah, sir has been given the
Yes.
presenter rights. Yeah. So you can just share your screen, sir. Good afternoon.
Hi, my name is Rajesh Yadav, and I will share just now. I'll share my screen.
Yeah.
So
Welcome, Mr. Rajesh Yadav. Good afternoon.
Good
yeah,
afternoon,
meanwhile,
madam.
Loxi, you can start the formal introduction.
Yes, ma'am. So our
Yeah,
next
so
session is an essential aspect of vacuum technology, contamination control in vacuum environments. We are pleased to welcome Mr. Rajesh Yadav, life member of ISHARE and Director of Engineering at Soneva, Maldives, with extensive experience in vacuum system and contamination control. Mr. Yadav has played an important role in ensuring clean room integrity, optimizing vacuum environments, and preventing process defects in semiconductor fabrication. In this session, he will discuss contamination sources, mitigation strategies, and best practices for maintaining high purity vacuum conditions in semiconductor manufacturing. Without any further delay, we invite Mr. Rajesh Yadav to take the virtual stage. Over to you, sir.
Thank you, madam. Just give me a time. I'm just
Yeah,
trying to
please.
connect. Mm, 1 minute. Wait, it's not happening. Anu, madam, can you please share because it's not happening? I don't know, something's wrong here with me.
So you can just open your presentation. The screen is already shared. You just go to your presentation and the
Okay.
slides will
Okay.
be visible to us.
Can you see my screen now?
Yeah. It was already shared. So you can just
Yes.
open your, go to your slide. Yeah. So it's perfect, sir.
It's
You
okay
may
now.
please start.
Yeah. Good afternoon, everybody. My presentation will be related to health and safety, mainly the health and safety related to human and process in the semiconductor industry, mainly the contamination control in vacuum environment. Basically my environment, my background is about the internal environment uh, of this vacuum environment. Basically, I worked on a large scale vacuum systems in at airport, IGI airport. This large scale vacuum system was for the food production unit. It was a multi-story high-rise building, and there was a uh, there was a trash chutes on each floors, and it was distributed to the entire building. And the each operation area like kitchens, bakeries, confectionaries, they put the biodegradable waste, and it collected separately and non-biodegradable separately. The vacuum environment is critical for industries such as semiconductor. We all know that aerospace, advanced material processing, pharmaceutical, and hospitals. Flight catering, I worked. The biggest vacuum suction system installed in Delhi, one is at IJ Airport, and the second one is at uh, Yashobhumi Convention Center. The sources of contamination basically are the particulate matters in the vacuum environment. The molecular contamination, the process generated contaminants, the operator induced contaminants, the pumping system, the human factors responsible uh, for the contamination in vacuum environment, and the environmental dust. We'll discuss them one by one in detail. The source of contamination, basically it's a human and the process both. The particulate matters, the surface of semiconductor are particularly vulnerable to contamination like dust, oil, mechanical debris, or abraded material from moving parts. This accumulate on the surface can create barriers or insulating layers that interfere with the electrical circuit. Improper handling or transfer of wafers or components. The molecular contamination is airborne. Molecular contamination is basically outgassing from chamber walls, seals, and lubricants. The residual gases like water vapor, hydrocarbons, oxygens, and airborne molecules. The airborne molecules are often called the AMCs, which can negatively affect the quality of manufactured wafers by introducing defects during the vacuum-based processing steps, even at extremely low concentration, due to this potential to react with the wafer surface and disrupt the desired material properties. The major concern in the clean room environment where ultra-high purity is crucial for producing high-quality semiconductors. The vacuum conditions enables precise control over the chemical reaction occurring on the wafer surface, crucial for achieving desired device characteristics. The sources of the contamination in the vacuum environment. The molecular contamination, the key points are impact on the quality, the sources of airborne molecular contamination like operators, chemicals used in the process, equipment outgassing, surrounding environments. The common airborne molecular contamination type is like ammonia, water vapor, organic compounds, and various other reactive molecules. The vacuum conditions enables the precise control over the chemical reactions occurring on the wafer surface, crucial for achieving desired device characteristics. This is one sample how the air circulated in a clean room, the written air as well as the conditioned air, because there is a air change is required to maintain the healthy indoor air quality. Written air mixes with the conditioned air, and fresh air also mixes at the plenum chamber. This FU is the fan flow units. I will discuss this in upcoming slides in detail. This is one sample where the outside air is treated first before mixing into the clean room with the clean room air. Vacuum conditions enable precise control over the chemical reactions occurring in the wafer surface, crucial for achieving desired device characteristics. The filtration is basically, there are two steps of filter, HEPA filtration and ULPA filtration. The high efficiency particulate air filter and the ultra low penetrating air filters. The vacuum system utilizes high performance pumps to create a low pressure environment which draws air and contaminants through the filtration system. The high efficiency particulate air filter and the ultra low penetrating air filters remove even submicron particles. The chemical filters are designed to absorb and remove specific chemical vapors and gases, often using activated carbon or other specialized media depending upon the chemical present in the process. This is a bit in details how the HEPA filter and UPA filter, and then the chemical filtration removes all the microorganism from the clean room air. This figure is in detail. The ambient air is introduced into the clean room after pre-treatment. There is a pre-filtration. There is an air washer. Air washer absorb the particulate matters, and then the air goes to the cooling coil. Cooling coil removes the water vapors, which is below the dew points. Then there's a multiple stage of filtration system, high performance filtration system. Then it mixes with the conditioned written air, the ULPA filtration system, and that's how it maintains the quality in the clean room. The sources of contamination, the process generated contaminant, the byproduct of deposition, etching, or plasma reactions. By streaming of oil and other fluids from pumps, the semiconductors are extremely sensitive to even minute amount of contaminants, which affect the performance of device. Mitigation strategies mainly are to maintain a very high level of vacuum to minimize the presence of contaminants molecules. Choose material with low outgassing properties for chamber components. Regular cleaning of vacuum chamber to remove the accumulated contaminants. The environmental control system of semiconductor manufacturing clean rooms, basically. It's a type of semiconductor environment. Is like critical tolerance on temperature and humidity is very important to maintain the right temperature and humidity in the clean rooms. The dry and traces of moistures in environment. There's three conditions for this. One is temperature, humidity, and the particular airflow. This was fun. The process generated contaminants. Impact on the quality. Reduce yield. Defect caused by contamination can result in rejected wafers. Performance degradation. The electrical characteristic of the semiconductor device can be affected by contamination. Adjusting process parameters to minimize byproduct generation. In situ monitoring by utilizing monitoring tools to detect and address contaminations. The process-generated contaminants. The sources of process-generated contaminants are chemical reactions during the process like CVD, unwanted byproducts from chemical reaction can be produced and deposited on the wafers. Outgassing from materials. The chamber, wall, seals, and other components can release absorbed gases into the vacuum, contaminating the process. Particles generated by physical process like sputtering and etching can generate particles that can settle on the wafers. Improper handling of wafers or materials within the vacuum chamber can introduce contamination. Now, next is operator-induced contamination. Even with the strict clean room protocol, the operators can shed microscopic particles from their skins, clothing, hairs, even the breath, which can settle on the wafer during the handling. These contaminants can disrupt the electrical properties of the semiconductor, leading to defect, reduced yield, potential devices short circuit. Even while wearing protective gears, potentially impacting the quality and functionality of the semiconductors device due to the sensitive nature of production process. Minimize contamination by proper clean room attire, strict procedures and monitoring and training. The proper introduction of contamination can occur by direct contact with the wafer, airflow disruption, improper gowning, and static charges on an operator body can attract particles on the wafers. The strategies for the contamination control are clean the chamber design and material selection, the vacuum system maintenance, indoor environmental quality, clean room integration, preconditioning and backout, advanced pumping system, clean and handling protocol, precision air conditioning. Since the indoor air quality is my core area, I just want to discuss in detail about how to maintain the indoor environmental quality in a clean room. For example, this semiconductor manufacturing clean rooms. These shows indoor air quality, thermal comfort, lighting, indoor air quality, ergonomic and functionality, water quality, indoor air pollutant like VOC and RSPM. You know, these pollutants, how they affect the human health is very important for to maintain the right quality of air inside the clean room. Basically, there are I'll just go to the next one. The chambers design and material selection. Use low outgassing material for chambers, seals, and components. Example, stainless steel, ceramic, or peak polymers, minimizing sharp edges or complex geometries where particles can accumulate. Design vacuum pumps and systems to avoid backstreaming or oil migration. The vacuum system maintenance is very important to maintain the health of the vacuum pumps. Regularly clean the vacuum chambers to remove residues, replace worn seals, gaskets, and O-rings with high purity, low outgassing alternatives. Service vacuum pumps to ensure proper operation and prevent backstreaming. The indoor environmental quality is very important. This includes the thermal comfort, example, temperature, airflow, and humidity. Lighting, indoor air pollutants like volatile organic compounds, the respirable suspended particulate matters, water quality, odor, indoor air quality, chemical emission control, and cleanliness, etc. This is achieved by highly specialized HVAC system with advanced filtration and monitoring system. The PMS the particulate matters measuring systems, the various devices fixed in the clean room where the semiconductors are manufactured, the real-time air monitoring where wafers are exposed, vacuum motor clean room air, the liquid particulate counter, the air monitoring and lithography area, the DI water plants, deionization water plants, gas monitoring devices. These devices are placed at various locations to monitor the indoor air quality. The clean room integration. Install and operate vacuum system in a clean room environment. Maintain air purity with HEPA and ultra-low particulate penetrating air filters. Use laminar flow hood or enclosure for handling sensitive components. These are the type of pollutants: toxic gases, combustible gases, organic solvents, acid and alkalis. These are the byproduct of the process in the process of manufacturing the semiconductors. Strategies and contaminations: preconditioning and bake out the preconditioned vacuum chambers by heating them under vacuum to remove absorbed water and volatile contaminants backouts. The degas components and materials before introducing them into vacuum environment. The basic steps are moisture absorption and saturation, steam formation during solid reflow, pressure buildup, crack propagation, and delamination and failures. Advanced pumping system. Use dry pump. Basically, the semiconductor manufacturing units, they use dry pumps, which is scroll type or screw type, or turbomolecular pumps. To reduce the oil-based contamination, install cryogenic or getter pumps to capture residual gases. Strategies for contamination control. Cleaning and handling protocol. Adopt strict cleaning protocols for all components entering in the vacuum system. Use tools and equipments designed to minimize particle shadings. Implement anti-static measures to prevent electrostatic attraction of particles. Specific cleaning challenges: submicron particles, then metal ion contamination, the organic residues, and the electrostatic discharge. These are some of the strategies of contamination control in the clean room. The strategies: the precision air conditioning is for the process cooling like pharma, IT server, semiconductor, where humidity control is of paramount importance. The precision air conditioning is used in semiconductor manufacturing to control temperature and humidity level. This helps to maintain the strict environmental condition needed to produce high quality products. This can maintain a specific operating environment with constant temperature and humidity, and can control temperature difference within 0.1 degrees Celsius or even higher. This controls humidity, maintains temperature, minimizes defects, and ensure consistent product quality. The best practices: component preparation, assembly protocol, operational practices, process optimization. The process optimization optimize the parameter like temperature, pressure, and gas flow to minimize the contamination by product. There are 10 ways to prevent cross contamination in the clean room. Clean surface regularly, introduce hand sanitizers, create a cleaning schedule, wear appropriate personal protective equipments, dispose of material correctly, use products in plastic-free packings, assign items for certain jobs, store items separately, use correct cleaning equipment. These were some of the steps to prevent the cross-contamination. The component preparation: ensure all components are thoroughly cleaned and vacuum compatible before assembly. The initial step of creating the building block for a semiconductor device by preparing a silicon wafer with a smooth surface, often involving processes like wafer silicon lapping, polishing, and cleaning, which set the foundation for further patterning and deposition of various material layers to form the desired circuit components. The best practices for preventing contamination. The key aspect of component preparation is wafer fabrication, cleaning, oxidation, photolithography, etching, deposition, and ion implementation. Assembly protocol: system in clean room using proper protective equipment, for example, gloves, gowns, and strict access control, regular cleaning and maintenance of equipment, advanced air filtration system, monitoring air quality and particulate matter counts, adhering to strict protocol for handling vapors and chemicals throughout the manufacturing process, contamination prevention in clean room. Some steps: positive pressure to push the airborne particles, the high efficiency particulate air filtration to remove contaminants, temperature and humidity control, access control protocol. The assembly protocol: clean room with strict access control and proper gowning, monitoring and quality control like particle counter to identify air quality contamination issues, surface analysis to detect potential contaminant of wafers, the gowning particles, full body suit, the gloves and face mask, regular gowning checks. The wafer handling protocol is minimize exposure, limiting wafer exposure to air and handling only in designated areas. The chemical procedures: strict protocol for handling chemicals to prevent spill and vapors. Dedicated tools: using specialized tools designated for wafer handling to minimize surface contamination. The best practices for preventing contamination is operational practices. Avoid overloading of vacuum chamber with materials that might outgas or produce particulates. Mainly focus on managing and monitoring highly precise control like wafer preparation, photolithography, etching, deposition, and doping, all within the clean room environment. The key aspects are equipment maintenance, the regular PPM to minimize downtime and optimize performance. Batch processing of wafers to trace variability between batches, yield optimize, and load traceability. Optimize parameter like temperature, pressure, and gas flow to minimize contamination by products. Process control like temperature, humidity, pressure, chemical concentration by using advanced sensor. The practice of analyzing and adjusting various parameters within the production process to minimize yield, efficiency, and quality by minimizing variations. The process of optimization: main aspects: the automation of control process parameters and reduce human errors, the predictive maintenance to predict potential equipment failure, the parameter control and precisely manage critical process like temperature, humidity, and pressure. The challenges in the contamination control is miniaturization of components, complex processes, material outgassing, cost versus performance. The complex process, multi-steps manufacturing process increase possibility of contamination. The disposal of semiconductors also have an advanced impact on environment, causing groundwater and air pollution and generating toxic wastes. So the water treatment, once the water is used in the semiconductor manufacturing, water is treated through the process. Material outgassing, the temperature or new material in advanced processing may introduce unexpected outgassing issues, potentially contaminating the wafer and impacting the device performance. A critical concern in creating clean room environment due to the need of extremely high purity level. The common source of outgassing are polymers, plastic used in packing, the wafer carrier or photoresist can release VOCs, adhesives and cleaning chemicals. Cost versus performance. The balancing the cost of high purity material and advanced system with operational budgets. The cost of producing a chip to the resulting performance capabilities. Achieving higher performance often requires more advanced and costly manufacturing techniques and material equipments. Miniaturization of components. The main features are clean room environment, ultra pure chemical and water, adhesive filtration system for air, gas and liquid, surface treatment, cleaning to minimize wafer surface contamination. The main challenges in semiconductor contamination control is diverse contamination source, example human hair, skin flakes, clothes, chemicals, airborne particles, equipment wear and tear. Detection limitation require sophisticated monitoring and detection system. Cleaning challenges. Cleaning without contamination is a complex issue. Prevent international contamination spreading to outside environment. Implementing and maintaining a robust contamination control program can be expensive. Operator training to minimize operator-induced contamination. Size of semiconductor is becoming smaller, making contamination control increasingly difficult. The self-cleaning chambers, coating or technologies to reduce the adhesion of contaminants, automated unit that clean non-volatile material deposits. The self-contained units, they have integrated in situ cleaning technologies, can be programmed to perform each process steps used for non-volatile material deposits. These systems have integrated exhaust gas treatment units. AI-driven monitoring, predictive analysis to identify contamination sources and optimize maintenance schedule. Utilize AI algorithm to analyze real-time data from production process, enable the early detection of defects, prediction of potential issues. The main aspects are predictive maintenance, yield optimization, defect detection, process control, anomaly detections. The green solutions for the future innovation, development of eco-friendly cleaning agents and low energy bakeout systems, transition to renewable energy, optimize water usage by recycling, use advanced material with lower environmental impact, smart manufacturing with AI to minimize waste and developing energy efficient chips, advanced cooling technologies system for sustainability, smart manufacturing with IoT and green nanofabrication technologies. These are some future innovations in semiconductor manufacturing. This has been already discussed in the previous sessions. I will not go into the technicalities. That's it. This was my last slide. Thank you so much.
So thank you to Mr. Rajesh. And I
Thank you,
request
madam.
Lok sir to take it forward, please. Also, the feedback for this session the link has been shared in the chat.
Mr. Rajesh Yadav, thank you for your insightful session on contamination control in vacuum environments. Your expertise has provided us with a deeper understanding of contamination sources, effective prevention techniques, and the importance of maintaining a clean vacuum process. We truly appreciate your time and valuable knowledge you have shared today with us. Thank you.
Thank you, madam. Thank you.
So we will take a break as our next session will start from 5 p.m. as per the schedule. So we can come back at that time. And meanwhile, we are also trying to resolve all the queries which we have received regarding the attendance. So I request all the participants to join us back around 5 p.m. Thank you.